Hey folks, we're just about done with triangles, so it's on to our final topic for the year, sequences. Now I'm going to introduce the terminology as we get to it, but let's start by defining what a sequence is. A sequence is any list of numbers that's following some sort of rule. And in particular, a term-to-term rule tells you how to get to the next number. So in the examples of the sequence we've got here, the first sequence, all it's doing to get to the next number is multiplying the previous number by 2. So our term-to-term rule will just be times by 2. For the one after that, we've got a plus 3 rule going on. So our term-to-term rule is plus 3. What about this one? 200, 100, 50? Yep, that's right. We're dividing by 2. What about the one after that? 2 to minus 4 to plus 8 to minus 16. We're not adding, we're not subtracting, we're not dividing, we're timesing by a negative, which is why the sign is flipping around, so that must be times by minus 2. And our very last one is decreasing by 10 each time, so our term-to-term rule is minus 10. Now we could obviously use this to come up with the rest of the sequence. We could say, well, the next one's 16 and then 19 here, but we want to be a bit smarter than that. But anyway, sequences start with looking at these term-to-term rules. Now there are a few special names for these things based on what the term-to-term rules actually are. There are other sequences than these three, but these are the three we're going to introduce this week. The first type is a linear or an arithmetic sequence, or sometimes called an arithmetic progression, which just means that your term-to-term rule is that you add or subtract a constant amount. So for example, you could have a term-to-term rule of plus 3, or minus 10, or plus 0.02. Those would all be arithmetic or linear sequences. A geometric is one where we're multiplying or dividing by a constant amount. So for example, times by 3, or divide by 7, or times by 0.0726. Those are all geometric sequences, or the term-to-term rules for them. And the last type we're going to talk about is Fibonacci. Fibonacci is the only sequence we do which is named after someone. I think he's a 12th century Italian dude. And a Fibonacci sequence is one where you add the previous two terms together. And we'll come to that in a second. So let's look at these 6 sequences. These are split into basically 3 groups. What would they be? Well, our first one goes 5, 10, 15, 20. So the term-to-term rule there is simply plus 5. That would make it a linear or an arithmetic sequence because we are adding a constant amount. We are always adding 5. What about 5, 10, 20, 40? Well, this rule is times by 2, and geometric is where you are timesing by 2. What about this one? 5, 10, 15, 25. Well, it kind of looks like we're adding 5 for a bit, doesn't it? Because we go 5 plus 5 is 10, plus 5 is 15, but then it doesn't keep working, and a rule has to work all the way through. So this is actually an example of one of those Fibonacci sequences, because we go 5 plus 10 equals 15, and then we go 10 plus 15 equals 25, and if we were to come up with the next term in the sequence, we go 15 plus 25 and we get 40, and our next one after that will be 65. So this is a Fibonacci sequence. What about the last 3? Well, there's one of each, so do you know which one is which? First one, 9 down to 3 up to 12. So 9 plus 3 is 12, 3 plus 12 is 15. Yeah, that is a Fibonacci sequence. 9 to 3 to minus 3 to minus 9. We're taking away 6 this time, aren't we? Yeah, because it's constantly getting negative. So this is another of our linear or our arithmetic sequences. And I suppose by process of elimination, the last one must be geometric, but is it? Well, 9 to 3, 3 to 1, yeah, we're dividing by 3. So this is a geometric sequence. So those are the 3 types that you could be asked to identify this week. We're going to focus, though, on linear sequences, as there's a lot more interesting things we can do with them. But before we get to that, we should probably mention the nth term and show how that is used. So the nth term is used to generate terms within a sequence without having to know the previous term. Essentially, it allows us to jump around or to pick the 100th number in a sequence or the 50th number in a sequence without having to know everything around that. So it's very powerful. And the way it works is it's a bit of algebra, like this, 4n plus 3, that we substitute in different values of n. Namely, if we want to find the first term, then we would sub in n equals 1. If we want to find the second term, we'd sub in n equals 2. If we want to find the third term or the fourth term, well, you get the idea. So how does that work here? Well, 4n plus 3. If n equals 1, then we're doing the sum 4 times 1 plus 3. That gives us the answer 7. If we're subbing in 2, we're doing 4 times 2 plus 3. 4 times 3 plus 3 for n is 3, and 4 times 4 plus 3. So we can get that the sequence looks like 7, 11, 15, 19. So if you were asked what's the first 4 terms of the sequence, you could say that. And you could keep going with that. You can see clearly the rule there is plus 4, which we'll come back to in a few slides' time. But yeah, you sub in different values of n. What about if we wanted the 50th term? Well, what we would do is we would sub in 50 for n. So we go 4 times 50 plus 3, and we get that the 50th number in this sequence is 203. What about if we wanted the 100th term? Well, we'd sub in 100. 4 times 100 plus 3 is 403. So yeah, it's a really powerful tool to allow us to go to distant points in a sequence without having to write the whole thing down. What about the same thing for 3n minus 10? Again, if we wanted to find the sequence, we'd need to sub in n is 1 and 2 and 3 and 4 to get the first few terms. 3n minus 10. So we're going to go 3 times 1 minus 10, and we're going to go 3 times 2 minus 10, 3 times 3 minus 10, and 3 times 4 minus 10. And that will give us our sequence, which looks like minus 7, minus 4, minus 1, and 2. And you can tell there that the rule is plus 3 if you wanted the term to term. 50th term, well, we go 3 times 50 minus 10. And we get ourselves out of that 150 minus 10, so 140. If we wanted the 100th term, we go 3 times 100 minus 10. And we get ourselves 290. And hopefully all that is seeming quite repetitive now. If you want to find something within a sequence and you have the nth term, then you just sub a value in. So I'd like you to pause the video at this stage. I'd like you to have a go at filling in the table that's in front of you. Again, we want the first 5 terms of the sequence here. So that means that we're trying to sub in n is 1, n is 2, all the way up to n is 5, because we want the first 5 terms. Okay, pause the video now. I'm going to go through them in 3, 2, 1. Okay, so I'm not going to show all of the algebra here because we did a lot of that on the previous page, but just so you can check your working. For our first term, first sequence rather, the 2 minus n, this would go 1, 0, minus 1, minus 2, minus 3. It's basically 2 and then take away increasingly large numbers. For our third sequence here, 2n minus 4, we would start with minus 2 as our first term there, and then it would go up in 2s. So we'd have 0, 2, 4, and 6. For our third one, it's a little bit different. This is going to go down, and our first term would be minus 2 again, but our next term will be minus 5, and then we go down in 3s. One after that, we've got an n squared plus 2n. Now this is probably worth talking about. So if you wanted to find the first term here, you'd need to be doing 1 squared plus 2 times 1, which would be 1 plus 2, which would be 3. For our second term, you'd want to do 2 squared plus 2 times 2. So we have to sub in n in 2 different places here. That would be 4 plus 4, that would be 8. For our third term, 3 squared plus 2 times n, that would be 15. And then our fourth term would be 24, I think, yep. And our fifth term would be 35. There is actually a pattern with that. It doesn't seem so obvious because it's going up with different amounts each time, but we'll look at that on the next sequence video. Something that people get wrong here, if we've got 2n squared, is to quite often multiply by 2 and then do the square. Bibmass wise, you should be doing your square first and then timesing by 2. So the first term here would be 34 minus 2 lots of 1 squared, so 2 lots of 1, which would be 32 as our first term. And then the terms after that, we'd be doing 34 minus 2 lots of 4, so that would be 26. 34 minus 2 lots of 9, so that would be 16, and then so on. So we go down to minus 16 as our last one there. And then our last one, minus 2 to the power of n, a little bit of a fiddly sequence. So this just means how many minus 2s we're starting by. So we'd start with minus 2, and then for our second sequence, we'd be doing minus 2 times minus 2, so that'd be 4. For our third one, we times by minus 2 again, and you can see it's just sort of getting bigger, and well, it's times it by minus 2 each time. It's a geometric sequence, that one. Okay, so let's talk linear sequences. So specifically, we're going to focus on the nth term of a linear sequence here. And a linear sequence, as we signed, or an arithmetic, is where the term-to-term rule is adding or subtracting, so plus 3 or plus 7 or whatever. So there are two things we need to do. We need to find what's called the constant difference, that's how much it's changing by, and we need to find something called the zero term, which I'm going to define on our examples here. And then our nth term just looks like dn plus c. dn plus c. So our first sequence, what do we need? We need the constant difference. So how much is it going up by? This is going up in tens. I can clearly see that. So d equals 10. What's our zero term? Our zero term is what would happen if you went back one. So what's before 3? So instead of plussing 10 to get to that, we're actually going to have to minus 10 and go back. And that would get us to minus 7. There are other ways of doing it, but I really do like this way of thinking about nth terms for linears. So our zero term is minus 3, minus 7 rather, and so our nth term is dn plus c, so 10n plus minus 7. Now you don't really want to write plus minus, so we'll just write minus 7. Okay, what about the next one? Well, we're going up in 0.5s, so that's our constant difference, and our zero term would be 0.1. So our nth term is 0.5n plus 0.1. We've got a positive zero term this time. And then the one after that, going up in 5s, our zero term would be minus 1, so it's 5n minus 1. Now we obviously don't always have a plus, we could have some minuses as well. So our next sequence is going down in 2s, and our zero term would be 17. Don't be tempted to take away 2 and go back down to 13. It would be going positively if we were going backwards. So d is minus 2, z is 17, this is minus 2n plus 17. What about the next one? Going down in 3s. Our zero term is 11, so d is minus 3, z is 11, so it's minus 3n plus 11. And what about our last one? Well, our last one is decreasing by 1s, and if our zero term would actually be minus 3, you can see if you go from right to left it's going down by 1 each time. So we'd have d was minus 1, we'd have z was minus 3, so this is minus 1n minus 3. Now you don't tend to have to write 1 in front of algebra, so you could also say minus n minus 3 there. Now you can be given fractions as sequences, which don't look linear, but they actually are. You just need to kind of split it into the top and bottom of the fraction. So let's show you what I mean here. We've got a sequence here, 2/3, 4/7, 6/11, 8/15, and if you were just to find the difference between these fractions, it's all over the shop. You get all kinds of crazy things with no clear difference. So what we do instead is we look at the top and the bottom separately. So our top goes 2, 4, 6, 8. So we find our constant difference, which is plus 2. We find our zero term, which is 0 actually in this case. And so that sequence would be 2n plus 0. Now you tend not to need to write plus 0, so we could just say our nth term is 2n. On the bottom of that sequence, we have 3, 7, 11, 15. That's going up in 4s. And our zero term would be minus 1. So our nth term is 4n minus 1. So our overall nth term then is the top is 2n and the bottom is 4n minus 1. That's all we do. We treat them as two separate sequences. So what about this next one? Well, the top goes 15, 19, 23. The bottom goes 14, 17, 20. We're going up in 4s. We're going up in 3s. Our zero term was 11, actually. It wasn't 12, was it? Our zero term was 11. And our zero term is 11 as well. So our nth terms are 4n plus 11 and 3n plus 11. So our nth term overall looks like 4n plus 11 over 3n plus 11. So yeah, fractions, top and bottom, do them separately. What about if our sequence isn't just numbers and isn't fractions, but it's actually a diagram or a drawing? It's graphical. Well, in this case, we just need to count them. So we want an nth term for the number of blocks for this first question. Well, let's count the number of blocks we've got. We've got 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then just find the nth term for that. That's going up in 3s. Our zero term would be 1. So our nth term is 3n plus 1. Next one says for pieces of wood in the fence, so count the pieces of wood. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's exactly the same sequence. That would be 3n plus 1 as well. Now there are a few ways we can turn this nth term around. We've already looked at the fact that we can find like the 100th term by summing in n is 100. But we can kind of do something a bit more clever than that and say, is this number in the sequence? We can do this using a little bit of algebra. So I've got a sequence here. I found the nth term as being 5n plus 4. And the question is 84 in this sequence? So I set up an equation. I say, well, what if 5n plus 4 was equal to 84? Does this work? How do I solve this sort of thing? Well, I want to take away 4. And that would give me just that 5n is 80. And then I want to divide by 5. And that would give me that n is 16. Now I've ended up with a whole number for n there, which tells me that 84 is in the sequence. And what I found specifically is that it's the 16th term. If I had n was like 16.3, well, I can't have a 16.3rd term in my sequence, so obviously that wouldn't be there. So is 84 in the sequence 140 minus 6n? Well, let's set up our equation. How would you do this? Well, let's do this a bit of an awkward way. Let's take away 140 from each side. We'll end up with minus 6n equals minus 56. We'll then divide by minus 6. And we'll get ourselves to n equals 9.33 dot dot dot. And as I said on the previous one, n needs to be a whole number for this to be true. We can't have something being the 9.3rd term in a sequence. So we can just go ahead and say no. Well, with the algebra, you wouldn't just be allowed to just say no. Lastly, is 84 in this sequence? Now we could carry it on forever and see how it goes, or we could use this clever way we've got. But we'd need to find the nth term first, so constant difference is minus 3. Zero term is 115. So this sequence is minus 3n plus 115. And then we need to do the same thing. Set that up. Equals 84. Do what we did on the previous one. Let's take away 115. We'll end up with minus 3n equals minus 31. And then we'll divide by minus 3 this time. And we'll get n is 10.3. So does that mean it's in the sequence if it's 10.3? No. We need a whole number for that to be true. And the last thing we can do here is we can find how long a sequence is. Technically, I guess a sequence goes on forever, but they've truncated them a little bit here. And for this, we need to do two things. We need to find the nth term, and then we need to use what we did on the previous page to find out where the last term is. So our sequence here goes 3, 7, 11 all the way up to 87. So let's find the nth term. Goes up in 4s. 0 term is -1, so that's 4m minus 1. And then we're going to set that equal to the last term, which was 87. And we're going to solve this, so we'll add 1, and then we'll divide by 4. And this tells us that the last term here is the 22nd term. So how many terms are in the sequence? 22. How many terms are in this sequence? To do the same thing, it's going up in 5s. Our 0 term again is -1, so that's 5n minus 1. Our final term is 229, so we'll set them equal to each other. Add 1, divide by 5, and that will tell us that there are 46 terms in that sequence. So yeah, decent intro to sequences. We're looking at some tricky stuff next time with quadratics, so make sure this all makes sense.